Hello, I'm Kawiki, and this is my beginner redstone tutorial. I'm going to go over how to use some basic redstone components. No assumptions made about prior knowledge besides a basic ability to play Minecraft. Um, you might be wondering why I'm staring at this redstone clock, because that doesn't really look very beginnery. And you would be right, there's an absurd amount of redstone behind that, although the actual concepts that make that work are pretty easy to understand, and I'm going to explain pretty much all of them. And it's all just built out of redstone dust, redstone repeaters, and redstone torches, and some blocks. And we'll look a little bit closer at that in a minute. First of all, there's two kinds of things that you start out with redstone. There's things that are sources of redstone power, like a button or a lever, are the ones we're going to primarily use now. There's also trap chests, redstone blocks, pressure plates, and then there's blocks that respond to redstone. We're going to play around with some pistons and redstone lamps. Iron doors or even other doors also kind of apply. And dispensers might be something that you're interested in. Um, but fundamentally, I mean, there's a few different things to do. You can put redstone power sources directly on your redstone components, and they'll directly power them, or you can sometimes put them next to them, or you can put them a little bit further away and connect it with redstone dust. It's kind of the most basic kind of redstone machine there is. A button works similar to the lever, except for it just turns on for a second and automatically turns back off. And then there's a couple of other things. So some people might consider a redstone torch to be a power source. It's sort of a power source, except if you power the block that it's on, the redstone torch turns off. And so that brings us to the topic of powered blocks. Typically, blocks that have a redstone power source adjacent to them, or have redstone dust that's powered going over them, the block that will then be powered, and it'll power adjacent redstone components. So, like that. And if I switch that thing, then the torch will turn back on, but the lantern turns off. And understanding that sort of idea of certain blocks being powered by redstone and certain blocks not being powered by redstone is kind of important. Redstone dust also just kind of connects to things that are next to it, but it doesn't go through blocks. So since I place that there, you'll notice that visually redstone dust no longer connects, and the redstone dust on top doesn't turn on, although it still does power the block because it's going straight into it. Now, the next thing that is useful to understand. Oh, and speaking of powering blocks, if you have a powered redstone torch, the block above a redstone torch, if there is one, will also be powered. And then we'll power redstone components adjacent to it. You can kind of use that if you wanted to have a signal that goes vertically. If there's ever a reason to have your redstone lines go directly up like that, it can be a handy way to do that. You notice that they invert when I change the lever. So the next important component to understand is a repeater. A repeater is pretty easy to understand. So what happens is, when you have these sort of redstone dust lines, they only have so long that they will carry a signal. You notice it gets dimmer and dimmer the further you get from the lever, and it's actually the redstone dust adjacent to the lever or any other kind of redstone power source is going to have a power of 15. And then it goes down by 1 the further you get, and when it gets down to 0, you're no longer going to power anything. So this one right here is the last block that has any power. It has a power level of 1. If you put a repeater on the next block, it'll power that repeater, and the repeater brings the signal power back up to 15, basically continuing the signal. It also introduces a 1-tick delay, and tick is sort of nebulously defined, but normally a tick is about a 20th of a second if everything is performing well in the game. And if you use the redstone repeater in the same, whatever the I'm right clicking on it now, but depending on your platform, it's whatever you would use to push a button or open a door or whatever. You can add delay, so the maximum delay that a repeater can be configured to have is 4 ticks. And there are often reasons you want to introduce delay into your circuits. And so repeaters are a convenient way to do that. Torches also introduce delay. Each torch that the signal goes through has an innate, basically adds 1 tick of delay to, and that's not configurable the way it is with repeaters. Now, if you combine, let's say, a repeater in a circuit, and you'll notice when I use redstone torches, I tend to have them hang off of one side of the block because it's convenient for how they work with circuits. Notice that it goes back and forth and blinks here because I have sort of a unstable circuit here. I've added a delay so that it's not quite so fast. If you have a circuit that's unstable and blinks really quickly, then the game sort of assumes that it's a mistake and turns everything off. But if it's slower, it allows it. So, this thing is what's called a clock circuit because it turns on and off at regular intervals. In this case, I've got 4 ticks of delay on the repeater and 1 tick of delay on the torch. So there's 5 ticks of delay. It's actually 5 ticks on and 5 ticks off, so there's technically a 10-tick cycle on this clock circuit. And there are things that clock circuits can be useful for, obviously, like building clocks. Although there's probably fewer things that are extremely useful that you would use them for, it's nice to know how to build one. And one thing that's nice about, there's lots of ways to build clock circuits, but one thing that's nice about this particular one is that you don't have to seed the signal in any way. It just sort of always is going to be on and off, and you toggle between those because the torch will always change it to the signal that it wasn't before, or to the state that it wasn't before. Now, some extra little trick that you can do with repeaters is if you put another repeater into the side of a repeater, I'm going to take the delay off of the locked repeater now. It locks the repeater into its state, and it it'll no longer change even though there's something in between it. So basically the signal behind it isn't going forward because the repeater is locked. Now I'm going to go ahead and break some of this other connection. And if I have a button that basically turns off the repeater that locks the other repeater, you'll see that it'll start moving again, and then it'll freeze again when the button turns off. The button sets a signal for a certain number of ticks, and it's actually, I think, different between stone buttons and wooden buttons. It's a little inconsistent. You'll notice what happens here is that blinks a few times, and then it ends on the opposite state that it used to be. So now it's off, now the torch is on, now the torch is off again. But it's sort of imperfect because it's flashing back and forth for a little bit before it settles on the new state. But this circuit is kind of a useful little component called a T-latch in circuit design, or a T flip-flop. The T stands for toggle. And the idea is that it's actually a memory circuit that holds a state, and when you clock it, and again I'm sort of overloading this term of clock because it's the way that people who design actual real circuits in real life talk about this thing. When you clock the circuit, it switches states. Now let's make it a little bit cleaner so that it doesn't do that flashing on and off. And this is a circuit that's called a rising edge filter. Here's the basic idea. If you have one signal come in that goes through a redstone torch and through a repeater, when you click the button on the other side, it'll always be on because either the torch is on or the repeater is on. If you put a 1-tick delay on the repeater, then that gives you a 1-tick period of time where it'll be off and then it'll turn back on. The reason it's called a rising edge filter is if you sort of think of the redstone signal as like a graph over time where signal is low from the button when you're not pushing it, and then it goes high when you push it and then comes back down. This converts that into a thing where it turns off only for the tick it goes high and then goes back down. It doesn't matter how long the input signal is on, it'll always be off for 1 tick on the outside. Now, if for some reason you wanted it to be inverted, you have to put another, basically, I guess a true rising edge filter would just turn on for 1 tick. But because the locking mechanism on the repeater is such that the default state where you sort of don't change anything is with the signal on, it's actually more useful to leave it this way. And it's because it's just simpler and it does more what you want. And so now when you click the button, it'll toggle the state of the circuit. Notice the redstone lamp just turned off. Click it again, it turns on, and there's no turning, there's no blinking back and forth between stuff. Now this actually, these two circuits together, the T-latch over here and then the rising edge filter over here, are a really useful combination. I'll tell you why. How many people have done like a redstone hidden door with some pistons or something? So you do that. Let's see, we'll have that go up there so it powers both of them. And you have something like that, and then somewhere here you have like a doorway that it's behind, and then you click the button and it opens. Now normally what people do to power this is something a little bit stupider than this, where they maybe stick a button like that. It only does one of them, but you get the idea. Let's see. Or actually, I guess you do a torch here to invert that so it's closed by default. And then you sort of, you press that button and then you try and race your way in before it shuts, which is, works, but it's not ideal. Especially if you have to walk that far. Obviously, you put the button a little closer than I just did. But with this circuit, and the reason you do that rather than a lever is because how do you close the door after you go into the door? You don't want to leave it open. But if you do it this way, you can actually have, let's see, that's not a good place to do that. Let's see here. I'll just stick that on here because I kind of made this in a way that's a little convenient to get to. Alright. So we'll go back over here, we'll have that connect to that circuit, and we'll stick a repeater in just in case we need it. It's kind of far. Alright. Do that. You can close the door, you can open the door. And then back here, you have another button, say over here, that does the same thing. You can shut the door from the inside or open the door from the inside. From either side you can toggle this thing. So that's a much more classy way to build those mechanical hidden doors that people love to make so much on their secret bases. So moving along here, one thing that's nice about the T-latch is that, similar to the clock circuit we did earlier, it innately has two states, and it's always either going to be on or off, and it'll always put the opposite state automatically in the back of the locked repeater so that it's always the next state that you'll have. But conceptually you could actually make a much more complicated state machine with lots of lots of locked repeaters. So say for instance we do something like this, we'll do 4 states, and then I'm going to put 4 repeaters in there to lock it. And I'm going to set up that rising edge filter again over here. So don't forget to put the 1 tick delay on that. Alright, and then have our input. We'll have a button here. So, and then of course we'll do this and we'll put them in a loop here. Let's see. So let's have those 4 in a loop. And so the idea is that there will be a signal that turns on here. I'm just going to go ahead and start the signal here. And so the one problem with these bigger state machines is you have to seed it with a state. So I'm going to have a lever there that puts a signal in going into this one, right? And I'm going to hit this button, which will simultaneously basically allow each of these things to go, and then I'm going to turn this off. So now we have exactly one of these 4 locked repeaters that's on. We push the button, it unlocks all of them for 1 tick, and it advances it to the next state, and again to the next state, and again to the next state. And then you notice now this line is lit over here to go back into the first one. We click it one more time and it goes into that first state again. So this is a 4-state state machine. And there's plenty of ways you could do the input to this. You know, I'm using a button here. If we did something more like a clock circuit like we had in the beginning, let's see. And actually, let's make put 2 4-tick repeaters in here. Now I've got a 9-tick delay between these, or an 18-tick total cycle length. And notice that because it doesn't matter how long the signal is on, it will always filter it down to 1 tick off after this part. This will just keep working correctly with first state, second state, third state, 4th state. Since we have an 18-tick cycle, that's a little bit faster than 1 second per state. Now, exactly the same thing is happening here as is going on behind that clock. We just have 3 of those state machines. The one on the right side ticks every second-ish. You know, it's actually exactly like this one where it's an 18-tick cycle. And there's 10 states, you know, from 0 to 9. The second one has 6 states from 0 to 5. And then the third one controls the first 2 digits, and it has 12 states. And the idea is that when you go from state 9 to state 0 on the right side, that is the input that clocks the second state machine. And then when you go from 5 to 0 on the tens digit there, that's where the signal comes from that clocks the first part of the time. I guess sort of the hours, although it's approximately a minute for each hour in this case. It's not true hours. And so that's kind of what's happening behind the scenes up there. And let's actually go up and look at it here really quick. So, thing number 1 here, this is the actual clock circuit here. Like I said, it's identical to what we were doing before. 1 torch, 2 4-tick repeaters. This line goes to the little colon in the middle to make that turn on and off. We actually don't want that to be filtered. We just have it turn on for 9 ticks and off for 9 ticks. This filter then ticks this state machine, and it's important that all of these repeaters the lock and repeater is unlocked simultaneously, or else the state will get lost somewhere in there. So you notice it's moving one tick at a time over here. And what these are doing is it's powering this redstone torch. So one of these is turning off at a time. And I'm using redstone torches kind of in this alternating pattern here to move the signal up in a way that doesn't interfere with each other. It's kind of just a space thing, but it causes a lot of delay in the circuit, which I have to make up for later. And then these torches on the outside actually determine which parts of the display are on for each number. So basically if there's a torch here, then for this number this is 1, so you notice there's only 2 torches that are facing out on this particular digit. And they correspond to the ones that power these things. Now something to understand here is that I'm directly using the repeater to power the center redstone lamp, and that is powering the 2 neighboring redstone lamps. Sort of kind of using that powered block concept to make each segment. And then in engineering they call these things a 7-segment display because there's 7 bits to the numbers that can be either on or off that causes the numbers to show up. Now these repeaters here, you notice there's 3 4-tick repeaters here to cause 12 ticks of delay. Here there's 2 4-tick repeaters and 1 2-tick repeater for 10 ticks of delay. This one has 8 ticks of delay, 6 ticks, 4 ticks, 2 ticks, and 1 tick because I just need to be able to continue the circuit or else it'll die before it gets there. So it's not exactly in sync, but this is basically to make up for the fact that for each level I'm going up I have 2 torches creating 1 tick of delay. So this makes it so that the number changes kind of all at once. But the state in the background is actually quite a bit, several ticks ahead of what you're seeing on the display. And then this part here, this will turn on when we're going between 0 and 1. I guess when we first go to 0 is when this will be on. And then that goes through. This is another rising edge filter. And then it comes around here and clocks this 6-state machine, which is the 10 minutes state. And then this one is actually the one that lights up when we go to 0 on the 10s, and that goes under here kind of down a floor for a second. Hopefully that's not something important. And that clocks the 10s digit. Now the 10s digit is a little bit complicated because I just couldn't place this rising edge filter in a place where it would reach all 12 of these locking repeaters. And so instead I have it go through I have it go through this repeater that's a little bit further and closer to stuff, and I think it just barely reaches. I actually thought I had 2 repeaters, but maybe it's just the one. But regardless, and also I put one of the locking repeaters up here because it has to go across so much space here, and I did that I think probably with all of them, so that basically there's not a locking repeater over here, and instead it's just up here coming back the other way. Yeah, that's kind of the basic idea, and then these have a repeater in the middle because otherwise the later numbers wouldn't make it all the way to the display. So that's how the clock works, and that's pretty much all I have to say on this. So goodbye.